Hello, everybody. I'd like to welcome you to this interview, which is featuring an author from a recent prefatory chapter of the annual reviews of Astronomy and Astrophysics. These prefatory chapters highlight the careers of certain individuals who have played an exceptionally large role in the history of modern astronomy. My name is Sandra Faber. I'm an astronomer from the University of California, and I'm also co-editor of the Annual Review of Astronomy and Astrophysics. Our guest today is Maarten Schmidt, retired professor of astronomy at the California Institute of Technology. Maarten has had an almost unbelievably productive career as an observer using mainly the Palomar 200-inch telescope. His most famous accomplishment was identifying quasars, small but brilliant sources that we now know are mass-devouring black holes at the centers of galaxies. For this and other accomplishments, Maarten has been awarded virtually every major prize in astronomy, including the Bruce Medal, the Kavli Prize, the AAS Russell Lectureship, and the Gold Medal of the Royal Astronomical Society. I think we're in for a real treat today as we listen to Maarten's account of some of the most exciting years in the history of astronomy. Welcome, Maarten.
Thank you, Sandy.
So I've already introduced the notion that you've discovered quasars. This is a wonderful story, and I wonder if you could sketch it briefly for us. Take us back to maybe 1960, when radio sources were being discovered, and among them were these peculiar star-like objects that nobody understood.
Yes.
Mm-hmm.
Yes, that object in 1960 was 3C48, which was identified with a stellar object of 16th magnitude, comparatively bright, and of which the spectrum showed a number of features that could not be understood at all. The astronomers are always willing to speculate, and I remember once doing a session with Jesse when we were wondering what it could be.
That's Jesse Greenstein.
Jesse Greenstein at Caltech. I once remember at lunch that he started to speculate that perhaps these lines came from enormous redshifts, that is, from X-rays, all the way into the optical. And the curious thing is, of course, that eventually we found that quasars do have redshifts, but not huge ones, but sizable ones.
Very sizable. Mm-hmm.
The first case of 3C48 remained understood for a number of years.
So let me just interrupt there and say, or ask, that was basically Greenstein's work on 3C48? You were not yet involved?
I was not yet involved, and just about everybody at Caltech seemed to be in it. Jesse Greenstein,
Tom Matthews?
Tom Matthews, of course, yes. I think Sandich may already have been involved too at that time, I think.
I think so. Yeah, he was measuring brightnesses, I believe.
That's right,
yeah.
That's right.
Mm-hmm.
And that's a good point you're making, because what happened was that Sandich found that the thing was variable in time.
Mm-hmm.
Now, it's easy to realize that if something changes substantially, like by a factor of 1.5 or 2 or so, over, say, full month, that its diameter cannot be more than 4 light months. That seemed to indicate that it was a star. It was very small.
Exactly.
So the problem of understanding these emission lines in its spectrum was just dormant for a number of years. In the subsequent years, there were other radio sources that were also identified with stellar objects, but they didn't have many lines. There was one object that had one line. I published it immediately in the Astrophysical Journal letters, but of course it told you nothing.
Let's go back just a second and have you tell us about how you got involved in this game. You're pretty recently arrived, youngish, professor from the Netherlands.
That's right.
And now you've got the 200-inch at your disposal.
That's right.
That must have been a thrill.
That's right.
Mm-hmm. So how did you decide to go into this area? Because you'd not been working on radio galaxies that intensively in the past, right?
Well, actually, I had been working with Tom Matthews, taking over from Minkowski, in the identification of radio sources.
Okay, maybe we should say a word about who Tom Matthews was.
Tom Matthews was a postdoctoral fellow and a staff member at Caltech, and he worked on the radio sources at Owens Valley with the pair of 90-foot antennas, I believe, in going through the catalogue of our Cambridge, England colleagues called the 3C catalogue, and made the positions uniform and much better than they were up till that stage. And then he gave the position. At the position of the source, he gave me a finding chart where I saw the stars in the sky and a cross where the radio object seemed to be, and a suggestion for which might be the identification. Worked on that for hard, but once in a while there was a stellar object that came up. I had nothing to do with 3C48, but there were other objects that came up. Once in a while, there was just a source that seemed to be stellar and showed either no lines at all or one or two lines. And we didn't understand anything.
Did you feel as though at this point you were getting some understanding of some of these sources, like they were galaxies? A lot of them were radio galaxies. Some redshifts were being measured. At least maybe that side of the puzzle.
Those were the radio galaxies.
Right.
But those that looked like stars in the sky, I just considered as stars. I didn't consider them some type of radio galaxy. They were for a while even called radio stars.
Exactly. Yes.
So that lasted until 3C273.
And a date might be interesting.
That was in August 1962, that the first observations were done in Australia of occultations of this very bright source in the sky. I think it's the 11th brightest source in the sky, radio source, organized by John Bolton over there.
And Cyril Hazard?
And Cyril Hazard.
Yes.
And Cyril Hazard was the prime younger man who did the work. And that led to positions, especially when there were several more occultations by which uncertainty about where the source might be were resolved.
We just might clarify and say that an occultation is an occultation by the moon.
Yes, indeed.
So when the moon goes across the source,
right.
You know where the moon is.
Yeah.
You can use that to tell you where the source is.
So it's clear. And so that led to positions that became more and more accurate. Now, in the case of 3C273, what came out of it was a very curious identification. There was at that position a 13th magnitude star.
Which is unbelievably bright.
Unbelievably bright. all the radio galaxies I was working on would be 17th magnitude, 18th, 19th, up to 20th. I could see down to the 20th magnitude at Palomar. He was a 13th magnitude star that was there. I thought it had to be eliminated.
Right.
So I think it was in the December 1962 that I took the first spectrum of it. I took it with a telescope rather way down, I think shortly before having to go to bed because the sun was about threatening to come up, and took a spectrum of it. And since it was so bright, I totally overexposed it.
Had you ever observed anything that bright before?
No. The thing I observed were typically 100 times fainter or more.
Right.
And you would observe them for many, many hours with a photographic plate, which is, of course, slow. So I took a spectrum of it, and it was totally overexposed. There was something funny, however, because in the ultraviolet, it stopped very suddenly.
Really?
At
like a cliff there in the
at about 3250 angstroms. 3250. Normally you wouldn't see any light over there, but that thing was so bright, it was overexposed. So 2 nights later, I did an exposure that was, I was more modest in my exposure time.
Just tell us do you happen to remember what these exposure times were?
These were truly short that I finally took.
Like a minute or something like that?
No, it was after all photographic plates.
Yeah, okay.
So I still think, I can't quite remember, but they were probably still of the order of half an hour or so.
Half an hour,
yeah.
Okay.
Those plates they had a very low quantum efficiency. So when I did that, I saw a number of lines. And I went home and I measured the lines, their wavelength, and I got of the order of 3 or 4 lines that seemed to be real. And I took the list. I took it to Ira Bowen.
Why Ira? First of all, who was Ira?
Ira Bowen was the director of the observatories at the time, and a physicist, came from Caltech to guide the observatories, and he had done an identification of mysterious lines in particular nebula in 1926 that were temporarily called mysterium, but actually were due to a process that he illuminated, and it was fully okay. So
he was your resident expert.
Yeah, right. So so he didn't come up with anything. There was a line at 4600, and I mean, I think there's a helium line at 4686, and it sort of got the attention and so on. But then nothing else worked. One line, if you took it, then the others made no sense. So I left it for a while.
Like a week or two, or a month, or something like that?
I think it was December 62 I had taken the spectra, and it was, I think, in February, yes, that I looked. Oh yeah.
You were writing a paper.
Searle had said, why don't we? And John Bolton was organizing it, and Searle was going to write the first paper. I would write the second paper about a second follow-up paper about my optical results, which weren't there yet. And that didn't take long, however, because just to Because when I wrote the article in words, I said that they were regular in appearance. The spacing was regularly changing from right to left, red to blue, and that they also become fainter from red to blue.
Yes.
And for some reason, I decided to make an energy level diagram. And I'm not that kind of an astrophysicist at all. I didn't know what I was doing.
Yeah.
It seemed from the exercise that things were not regular. I said, oh, come on. I mean, they are regular. I see that myself.
So you were making some arithmetic mistake.
Must have.
Yeah.
So I said, okay, I'll show you how regular it is. I'm going to compare it to the Balmer lines.
Yeah.
So I took the line most to the red, divided it by 4861, the next line by 4340, and the ratio in the first case was 1.16. The second one was 1.16.
Right.
And the third one was 1.16.
Bingo.
I was looking at the Balmer spectrum shifted by 16%.
So it's interesting that you invoke the Balmer lines, not because you thought necessarily that these features were the Balmer lines.
No.
But you just wanted to use the Balmer lines as a template.
That's right.
For some regular sequence.
You don't find lines like that, like the Balmer lines in just stars. And it was a star. And that's the question that is often asked. Did you realize that it was a galaxy? No, it was a star.
A star with a strange redshift.
Exactly.
So then what happened? I mean, like in the next minutes after you got your result, then what happened?
I stormed out of the room of my office. I went to Jesse. Said, Jesse, I got a redshift for 3C273. Oh, Jesse says. Now, Jesse had written a paper about 3C48, and he had, in his usual fashion, unpublished, he had, in his usual fashion, speculated about what certain lines might be. And it turns out, if you look at the unpublished paper, one of them is 0.35 for the redshift.
One of his speculations, right.
Yeah. But for various reasons, he had spectroscopic reasons, he had, one of them was that he found that if he took the redshift that it finally turned out to be, that if he took that there would be a large range of energies in these lines, energy range, ionization.
A range of different ionization
enormous,
states.
Yeah, enormous.
Okay.
And he forgot that Cygnus A has neon 5 and N1.
Yeah, So that had already been seen.
Of course.
Yes.
If only he had remembered that, we understand, of course, why that is all, but because of, it's not a stellar distribution, but it's a very wide synchrotron distribution or whatever. And
also, he had only 2 lines.
No, there were a large number of lines, not all real. That was the trouble. He went quite far down, digging in. There were of the order of 3 absolutely real lines, I think, in 3C48.
Okay.
Yeah. So there we found that, yes, it came out, and we were so excited, and we made so much noise in Jesse's. And the interesting thing was that in his spectra, which had a larger redshift, of course, than 3C273, when you looked at a line at the lowest wavelength, it turned out to be that magnesium-2 doublet of 2800.
Right.
And when we looked at a redshift of 273, that sudden cutoff at the end was
that feature.
magnesium-2. So there was already a confirmation where the one supported the other. So as I say, we made so much noise, and Bevo came and wondered what was going on. So as I must have written somewhere, probably for you, that we all trooped off to his house, and we surprised Naomi by dropping in the house and yelling.
We need a drink.
And we need a double of whatever is in the house, we said.
Right.
And I can tell you that the next day we spent much of the morning just trying to get out of it.
Mm-hmm.
Was there any chance that and Jesse liked things like that, but we couldn't, and we finally realized this was it.
So by realizing this was it, today, to an astronomer today, if you say the word redshift, the first thing that's going to leap into their mind is the cosmological redshift, and therefore that these quasars were quite distant because
Yep.
they had big redshifts.
Yep.
But you've just stressed a few minutes ago the fact that you, as you were measuring this redshift, were still thinking of this object as being a star.
Yeah.
And we know, or we thought, that stars could also have redshifts.
True.
Caused by gravity? A gravitational redshift? So is this what you were thinking about that second day, trying to rule out the gravitational redshift?
The gravitational redshift, well, there is of course the possibility of a motion redshift due to motion in the galaxy.
Okay.
But that cannot be more than the escape velocity of 600 kilometers per second.
Good point. Mm-hmm.
Which is only 0.002.
Mm-hmm.
And that doesn't get you anywhere. We need 16%. So there was no escaping it, essentially, that it had to be a cosmological redshift. Although, as I say, Jesse spent the next morning just exploring all possibilities. Now, the possibility that it was actually not a redshift, but a gravitational redshift came to mind.
Mm-hmm.
And I think I may have met Feynman, actually, on the, and I must have said, Dick, you won't believe what happened. And I think he said, oh, what about the gravitational redshift, he said. So, yeah.
Huh.
So that was worked out.
Who did that?
I did that.
I see. Uh-huh.
We knew from the lines that the electron density was only of the order of 10 to the 6, in 3C48 of the order of 10 to the 4, from spectral arguments.
Mm-hmm.
And of course the lines had a certain width, so you apparently had a shell around a massive object.
You had not one gravitational redshift, but a range, because the lines were broadened.
True.
Yes.
Mm-hmm. But the gravitational redshift does go as 1/r.
Yeah. So you had to have.
So so the thickness of the shell could be derived from the width of the lines.
Exactly. Mm-hmm.
So now I went through a calculation that I said, what is the mass of that central thing? So I first made it the solar mass. Well, then, of course, as you know, the gravitational radius of the sun is 3 kilometers. So it's of the order, of course, of a fraction of that, say 10 kilometers up the other way around. Mm-hmm. So it would be a 10 or 20 kilometer, perhaps neutron star. So that was a possibility that was considered.
It's true, but 3C48 was even larger, so
That's
you had
right.
to deal with that.
That's right.
Yeah.
And not only that, but I then went through an exercise in which I made the mass totally unknown of that central thing for a gravitational redshift. And by the time that I made it of the order of 10 to the 9 solar masses or so, it would have been at a distance from us of a number of kiloparsecs, and the whole rotation curve of the galaxy would have been distorted on both sides, one compared to the other.
Yeah, that's interesting.
And that could be ruled out all very pleasantly, and in fact was only done once by somebody else, I think. It was so decisive that we knew we had it.